We will now put together the ideas we've been going over in an example that we do by hand just from looking at a dot plot, since that's what we'll pretty much be doing on tests. We don't have software available to get that confidence interval for us, so sometimes we just have to go to these principles of counting dots. So looking at this example here, we have a lie detector that failed to detect a lie in 17 out of 48 trials. That's kind of alarming. We're going to consider these trials to be representative of all lie detector tests, so we investigate the reliability. The statistic here is a sample proportion, p hat, which is 17 out of 48. And that comes out to 0.354. The proportion, the population proportion that represents, we'll call P, and that is the failure rate of detecting a lie for all lie detector tests. We'll say among all lie detector tests. I'm clarifying the failure rate of detecting a lie because the other kind of failure would be to indicate that something's a lie when it's not, right? So we're just looking specifically at the failure rate of somebody is lying, does the detector catch it? Now looking at this Bootstrap distribution here, if we want to find a 95% confidence interval using a standard error and margin of error kind of technique, then all we need to look at from this is our estimate of the standard error, and we have our sample statistic. So we're going to say sample statistic plus or minus margin of error. And again, that margin of error, because this is a 95% confidence interval, the distribution looks reasonably bell-shaped. It's not perfect, but it looks good enough. So our margin of error is 2 times the standard error, which is 2 times 0.071, which is 0.142. And then our sample statistic, p hat, plus or minus that margin of error, is going to be 0.354 plus or minus that 0.142. I would subtract to get my lower bound of 0.212. I would add to get my upper bound of 0.496. So this is my confidence interval based on calculating margin of error from standard error. Remember also that I use the sample statistic as the center. I do not use the center of the Bootstrap distribution, even though it's a very close value. 0.352 is not exactly 0.354. 0.354 is really what I want to use here. Now I can also do this using percentiles. So the first thing I need to do is figure out how many dots should be in each tail. So if I have 100 samples, which I can see right here, 100 samples, and I want a 95% confidence interval, then I want to start by thinking 5% of 100 is in the two tails combined. So that's 5, and that tells me that we'd have 2.5 dots in each tail. At first you might think, well, half a dot, that's kind of hard. Turns out it's actually a little bit easier than having whole dots because you know exactly where that boundary is. So here's what we're going to do. Coming into our graph, 2.5 is going to get us halfway through this next dot. So I know that my left bound should be right in line with this bar here. It's between 0.20 and 0.25, looks a little closer to 0.25, so I'm going to call it 0.23. Now counting 2.5 dots, that's going halfway through the third dot on the other side. That also indicates that I am directly under this bar. That's between 0.45 and 0.5, a little closer to 0.4, a little closer to 0.5, so I'm going to call it 0.48. So an estimate for this confidence interval is from 0.23 to 0.48. And we can see that that is pretty close to the estimate I got using the standard error and the 95% rule. And there's no such thing as too much practice interpreting confidence intervals. So let's go ahead and just interpret the second one. It doesn't really matter which one we interpret here. They're both very close to each other. We'll start by thinking about what it means. The population parameter P is between these two values. And now we just need to think about what P represents. Remember, we defined P up here to be the failure rate for detecting a lie among all lie detector tests. So this means that that failure rate is between these two values. We'll express them as percents. Often when we're interpreting a confidence interval for a proportion, expressing it as percents might be a little bit easier to understand. So the failure rate for detecting a lie among all lie detector tests is between 23% and 48%. So don't count on that lie detector test to save your marriage, right? So real quick, let's see how to do this in StatKey. We just did it by hand, but we had to be given a dot plot to do it by hand. In StatKey, generating things for proportions often feels a little bit different from generating any sort of dot plot for other statistics, because the proportions usually don't rely on a data set so much. They just rely on a single proportion. So we'll start at Bootstrap confidence intervals, CI for single proportion. We have to click on Edit Data in the first step and enter the 17 and the 48 so that it knows where to start. Then we'll go ahead and generate 1,000 samples and click on two-tail. We'll see how close we come to what we got from our graph and from our estimate doing that. So in StatKey, CI for single proportion, edit data, I'm going to enter a count of 17 and a sample size of 48. And then I will generate 1,000 samples. And this is an example of, a little bit of an example of how the dots tend to stack up on individual values. So it's slightly less reliable of a confidence interval than you'd get if they were really able to fill in those gaps. When I click on two-tail, then I get an estimate from StatKey for this confidence interval. Looks like 0.219 to 0.479. Looks pretty close to ours. This is more like 0.22 to 0.48. We had 0.23 to 0.48. So we had a very slightly narrower interval, but it was otherwise pretty close.